In the previous lecture, we finished chapter 4. We now have chapter 5, which is about vector valued function and vector fields. In this chapter, you have two sections. In the first section, we talk about vector valued function. And in the second section, we have scalar and vector fields. First, we have a revision of vectors. We say a vector is a quantity which has magnitude and direction. A vector is a quantity which has both which has both magnitude and direction. Here we say a unit vector is a vector whose magnitude is 1. If the magnitude of a vector is 1, we say it is a unit vector. Unit vector can be shown here. Okay. Unit vector u, which is in the same direction as v. So if we have given a vector, if we want to find the unit vector which is in the same direction of the given vector, is v dividing by the magnitude of v. Magnitude of v is the square root of v1 squared plus v2 squared plus v3 squared. Okay, this is the magnitude of v. We divide each component of v by the magnitude of itself, and we get the unit vector. Here, this is the unit vector. A unit vector can be obtained from a given vector by dividing the vector by its magnitude. Standard unit vectors are I, which is the unit vector in the positive x-axis direction, and j is a unit vector in the positive y-axis direction, and k is a unit vector in the positive z-axis direction. Here, if you have given this vector, this is a vector, it's not given that it's a unit vector, okay? Then its length or magnitude is, length and magnitude are the same. It is v1 squared, we just square all the components for vector v, it's v1, v2, and v3. We just find the square root of each component, and then we find the sum of them in a square root. So the square root of v1 squared plus v2 squared plus v3 squared. This is the magnitude, or we can say it's the length of vector v. If vectors a to be a1i plus a2j plus a3k, and vector b to be v1i plus b2j plus bk, then the dot product of those two vectors, the dot product of two vectors, can be obtained by these two rules, any of these. The magnitude of the first of one of the vectors multiplying by the magnitude of the second one times cosine theta. Cosine theta is the angle which is between these two vectors. Theta is an angle that you obtained from the vectors. It's the angle between these two vectors. Or we can use this rule. a1b1 plus a2b2 plus a3b3. We multiply each corresponding components. Here we have vector a, which is a1i plus a2j plus a3k. And b is b1i plus b2j plus b3k. This is b3. Okay, we multiply the I components plus j components plus k components. We just multiply these and then we find the sum of them. This is the dot product of two vectors. This is the dot product of two vectors. You can use either these two ways. And the cross product of two vectors, we use this rule. Here we find the determinant for this matrix for I, j, and k. The first row must be I, j, and k. And in the second row, we write down the first the first vector components. Here, the components of vector A are A1, A2, A3. A1 beneath I, A2 beneath J, and A3 beneath K. Here, we write down A1, A2, and A3. Then for B, the same. For B, for vector B, we have B1I plus B2J plus B3K. This is B3. We write down B1 for I, B2 for J, and B3 for K. As you see here, B1 for I, B2 for J, and B3 for K. Now we find the determinant of this matrix. Yeah, we find the determinant of this matrix. The determinant of this matrix, we take the first row. You see, we remove these two rows and columns. We remove column 1 and row 1. And then we say it's I times multiplying these two minus multiplying these two. Okay? It's A2 B3 minus B2 A3 plus. So it's minus. Here, for the second one, for J, we remove these two. And you get A1 times B3 minus B1 times A3. It's minus J, A1 B3 minus B1 A3. Then plus. For K, we remove these two rows and columns. We get A1 B2 B1 A2. You get K, A1 B2 minus B1 A2. This is how to find the cross product of two vectors. Or you can use this way, this rule. Here, you find the determinant of this matrix, and you get A2 B3 minus B2 A3. It's the same as we have written down there. Times I minus A1 B3 minus B1 A3 times J. Then K times the determinant of this matrix. So we get the cross product of two vectors by this way. Look, in the dot product of two vectors, we get only one value. We get only one value. We don't get a vector. The product of the dot product for the above one, the dot product of two vectors is not a vector, but the cross product of two vectors is a vector. We must get a vector in cross product of two vectors, but for dot product, we don't get a vector. If all components of a vector are constants, if all components of a vector are constants, we say it's called a constant vector. For example, A equals 3I minus 2J plus 4K. As you see, all the components are constants. We say that's a constant vector. That's a constant vector. But if you have variables, we say it is a vector valued function. It's a vector valued function. For example, this one, if you have a parameter t in the vector, we say it's a vector valued function. It's 3ti minus 2tj plus 4 minus tk. As you see here, you have parameter t. So this vector is called a vector valued function. But if all components are constants, we say that is a constant vector. Here, in general, A of t equals f of ti plus g of tk plus h of tk. Okay, these are functions of t. These are functions of parameter t. this vector is called a vector valid function, because here we have parameters for the components, because all the components are not constants. Then we say a curve in a space can be represented as a vector valued function. Curve in a space, it could be represented as a vector valued function. For example, R of t is, this is a vector. Vectors can be represented either in this way or in this way. Both are the same. Okay, you can represent a vector either in two angle brackets or in this form. Okay, here f of t, comma, here g of t, comma, h of t. This is in two angle brackets. It's between two angle brackets. This is a vector valued function. And also this vector could be represented as this one. F of ti plus g of tj plus h of tk. The first component times I, the second component times j, the third component times k. Okay, in this form, which is between two angle brackets, we have no I, j, and k. We just write down the components and we separate them by commas. But when we write down it in this form, we must write down I, j, and k. We multiply the first component by I plus the second component by j plus the third component by k. And this is the vector. It's the same as the previous vector. Or we can write down as a parametric equation, as a set of parametric equations. The first component we denote by x, because in space we have x, y, and z. So the first component is x of t. We denote by x of t. The second one to be y. The third one to be z. That means here the first component here is x. The second component is y, and the third component is z. We say x to be f of t, y to be g of t, and z to be h of t. This is a set of parametric equations. Since t is a parameter, so g of t, f of t, and h of t are parametric equations. These are parametric equations. So this is a set of parametric equations. We say when t to be a constant, then the vector valued function R of t becomes a position vector or a constant vector. When you replace t by a, we get a constant vector, which R of a equals f of a times I plus g of a times j plus h of a times k. All the components here are constants. And this vector is called position vector. It's called position vector. If we replace t by a constant in a vector valued function, we say it's a position vector, which is also a constant vector. It becomes a constant vector because we replaced t by a constant. Here we have no parameters. We have only constants for each component. Now we have an example. It says introduce parameter t that relates the following functions so that the curve can be represented by a set of parametric equations. Here we have two examples. We need to find the vector valued function, for each of these two functions. And also, we need to write down the set of parametric equations. Here, May someone say, let x to be t. May someone else say, let x to be t squared. May someone else say, let x to be t minus 1. Choosing the parameters are not fixed. Choosing the parameters are not fixed. I choose x to be t. May someone else choose x to be t squared? It's possible. May someone else choose x to be a t squared minus t? It's okay. Choose any function of t. Any function of t. Okay. Here we let x to be t. How about y? So that means here x of t equals t. How about y of t? We replace x here. X is t, so we get y of t equals t plus 3, is it? We get t plus 3 for y. Y of t is t plus 3. This is the set of parametric equations. This is the set of parametric equations. Then the vector valid function is x of t and y of t. It equals to t and t plus 3. Or you can write down as ti plus t plus 3j. This is r of t equals to this. R of t equals x of t and y of t as the components of the vector. Then you multiply the first component by I and the second component by j. But be careful, the first component must be x and the second must be y. Okay. For the second example, y equals x squared. We let x to be what? X of t to be what? Give me a parametric equation for x. Anything. Let's say t plus 2. Okay. May someone else say it's t squared plus 2. It's okay. It's possible. Let's choose this one. Then y of t equals what? Equals to x squared. And x is t squared plus 2. We just square t squared plus 2. As I said, choosing the parameter equation, the parameters is not fixed.
So it's up to us.
Yes, it depends. It depends on yourselves. I choose t squared plus 2. You may choose to be t. Okay. Here, this y of t. That means r of t equals what? Equals to x of t and y of t. And this equals to x of t is t squared plus 2. And y of t is t squared plus 2 whole squared. This is the vector valid function. And also it could be represented as t squared plus 2i plus t squared plus 2 squared j. This is the vector valid function. Okay. It's easy. Do it by yourself. I said do it by yourself. Okay, do it. I mean, do it now. You can do it by yourself. It's easy. Now I have writing vector valid function for the curve in XYZ space. Here, in intersecting two surfaces or plane and a surface, we get a curve. The intersection of a plane and a surface is a line or is a curve. For finding equation for that curve, we can use parametric equations. We can use parametric equations for finding the vector valid function for that intersection curve. Here, we follow these two steps. We say the way to introduce t is not fixed. It's not fixed to use t. May someone choose t, another one choose t squared. It's okay, it's possible. And then the parametric equations are not unique because it depends on the choosing the parameter. So the parametric equations are not unique also. As you see here, these are the parametric equations. If someone else chooses x to be t, so how about y equals t squared? This is different from this one. Okay, that means the parametric equations are not unique. It depends on the choosing t, which means the curve can be represented with more than one vector valued functions. So the curve, which is the intersection of a plane and a surface, could be represented by more than one vector valued function. If in the exam you want to find, the line intersection or the curve intersection of a surface with a plane, may each of you get different results, get different answers. Okay, I mean all of them are true. Okay, here we have some examples, 3 examples actually. First one, it says find a vector valued function to represent the intersection curve between the hemisphere, this one, and the parabolic cylinder. We want to find the vector value function which represents the intersection of this sphere, this solid, and this plane or this cylinder. Okay, we are going to find the parametric equations or the vector valued function which represents the intersection between the graph of these 2 functions. Okay, we introduce t, the parameter. Okay, first let's write down the equations. Z equals for I, Z equals square root of 4 minus x squared minus y squared. And y equals x squared. We can introduce one of these 2 variables. Okay, we can introduce one of these 2 variables by the parametric equation. Okay, one of these 2. Y to be t, y or x to be something. Okay, it's okay. You can let y to be a parametric equation or x to be a parametric equation. You let x to be, let's say t. How about y? So y here, this is x of t actually. X of t to be t. Then y of t equals what? We replace x by t. We get t squared. How about z of t? Z of t is, we replace x by t, y by t squared. We replace x by t and y by t squared. We get 4 minus t squared minus t to the power 4. Because if we replace y by t squared, it's squared also, we get t to the power 4. These are x of t, y of t, z of t. Then the vector valued function r of t equals x of t, y of t, z of t. Okay, and is equals to the first component times I, or let's first write down it equals to t squared, the square root of 4 minus t squared minus t to the power. May someone else get different results? and both could be true. Here, this equals to Ti, the first component times I, T times I, plus T squared times J, plus square root of 4 minus T squared minus T to the power 4 K. It's I, J, and K. Here, because we have three components, the first component is I, the second is J, and the third is K. So this is the vector valid function, or this one is the vector valid function. This is the vector valid function, which represents the intersection of these two functions. No, that is for multiplying, for cross product of two vectors. It's for here it's minus. No, it's not. Here it's different topic. It's a different topic from the above one. That's for the first example. For the second example, it says find the intersection curve between the sphere and the plane, y equals 2. Here, we find the intersection curve. To find the intersection curve, we are going to find the vector valid function which represents the intersection curve. Okay? Yeah, it's for I, and for double I is x squared plus y squared plus z squared equals 13. And y equals 2. Here, we should find the vector valid functions, the vector valid function, which represents the intersection between this plane and this sphere. Okay, here in the example, it says find the intersection curve between this sphere and this plane. We are going to find the vector valid functions. To find it, what we do here, y is fixed, y is 2. So we cannot denote y to be a parametric equation. It's fixed, it's 2. So what else should we use? We can use x. We let x to be, let's say, t squared. Okay? Let x to be t squared. Then y is still, y of t is still 2, is it? It's a constant. So if x to be any parameter equation, y is still 2, because y is a constant function. Then z of t equals what? Look, z of t, we replace y by 2 and x by t squared in this sphere equation. In the equation of the sphere, you say z squared of t equals 13 minus 2 squared is 4, is it? Because y of t is 2, but here we have y squared. We move to the other side, becomes minus 4, and x is t squared. How about x squared? As t squared against squared, it becomes t to the power 4. This is z squared of t, but here we must find z of t. We take the square for both sides. We say z of t equals plus minus square root of 13 minus 4 plus t to the power 4. This is z of t. We now have x of t, y of t, and z of t. We just write down there between two angle brackets, which will be the vector valid function. We say r of t equals x of t, y of t, z of t, and this equals to x of t is t squared, y of t is 2, And z squared is plus minus square root of 13 minus 4 plus t to the power 4. And this equals to t squared I. This equals to t squared I plus 2j plus minus 13 minus 4 plus t to the power 4 plus t to the power 4 k. That's it. This is the vector valued function, which represents the intersection of this plane and the sphere. Okay. We have another example. It says find the vector valued function of the intersection curve between paraboloid, this is a paraboloid, and this plane. We need to find the line intersection function, or the vector value function, which represents the intersection of this paraboloid and this plane. First, let's write down the equations. This z equals x squared plus y squared. And x plus y equals x minus y equals 0. Here, to find the vector value function for the which represents the intersection of these two functions, what we do, we introduce a parameter t. Okay, we let x to be t minus 1, or x to be t, or x to be t squared, or x to be the square root of t. Okay, we let x to be t minus 1. Then y equals t minus 1 also. Is it? Y is t minus 1 as well. Let's say to be t to be easier. Okay. If x to be t, then y is t also. And z equals t squared plus t squared, which is 2t squared. Is it? It's t squared plus t squared, which is 2t squared. Then r of t, which is the vector value function, which represents the intersection of those two functions, equals x of t, y of t, z of t. This equals to x of t is x is t, t, 2t squared. And this equals to ti plus tj plus 2t squared k. This is the result. This is the vector value function. It's so easy, is it? So let's take a break for 10 minutes. Okay. Here we have sketching a straight line in the XYZ plane. We have sketching a straight line in the XYZ space. We say a straight line in space passes through a point A, which is A1, A2, A3, and parallel to the given vector. If we have a straight line which passes through a point and parallel to another vector, we say a vector valued function representing the straight line can be obtained through this formula. We can get the vector valued function, which represents the graph of the line, of the straight line, which passes through a point and parallel to this vector. It could be obtained by this formula. You say R of t is the vector valued function which represents the equation of the straight line. It equals to OA. This is the distance from the origin to the to the point. It's the vector from origin to the point which is given A. Here it's given the point A plus t times d. T times d. D is the vector which is given. We just multiply it by t, and then we find the sum of these two vectors. We get R of t, which is equation of the vector value function represents the straight line equation. Okay. In this type of question, in this subject, in this topic, to find the equation of the straight line, you have to given a point, and also the vector was parallel to the straight line. From these two, we can get equation of the straight line, or the vector value function which represents the straight line equation. Here we say R of t equals the vector from the origin to point A plus t times d, t times vector d. Here we have some examples. In the first example, it says sketch the straight line R of t equals 3 minus t times I plus 3t times j plus 3t minus 4k. And the position vectors R of 0 and R of 3. Here, we just need to sketch this straight line. We need to sketch this straight line. For sketching a straight line, we just need to pick 2 points on the on the line. Then we join them, we get the graph. In R2, we say if x to be 0, y to be, let's say, 2. Okay, we let x to be 0, we get y to be 2, and y to be 0, let's say x to be 5. We just look at these 2 points and we join them. This is the graph of the straight line. But in R3, here we have given a vector valued function. This vector valued function represents the straight line. It says sketch the graph of this straight line. Let's write down it. R of t equals, it says A, R of t equals 3 minus ti yes. Okay, and we need to find R of 0 and R of 3. Okay, here we say R of t equals 3 minus t, 3t, and 3t minus 4. The x component is 3 minus t. This is x. This is x of t. And this is y of t. This is z of t. Here we have x of t, y of t, z of t. That is, x of t is 3 minus t, y of t is 3t, and z of t is 3t minus 4. Here, x equals 3 minus t, y equals 3t, and z equals 3t minus 4. We have x, y, and z. Now, we just give two different values to t. Let's say t to be 0 and t to be 3. We choose the same as it's given, because here we can answer both parts of the question. Okay, so if you have no given r of 0 and r of 3, you can choose any two values for t, any two values for t. Okay, here we choose t to be 0 and t to be 3. T to be 0, then x is 3, y is 0, and z is -4. So the point is 3, 0, and -4. This is a point on the straight line. And t, let's say to be 4, to be 5, to be any value. Okay, here we choose t to be, let's say, 3. Then x is 0, y is 9, and z is 3 times 3 is 9, minus 4 is 5. So the point is 0, 9, and 5. Here we got 2 points. Now we plot these 2 points in R3. We plot these 2 points in R3. What we get? This is x, that's y, and this is z. Here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and also in the other directions. Okay, now we plot these 2 points. The first one is 3, 0, and -4. We always start from the origin, and then we count the units of x from the origin. From the origin, it's 3, 0, and -4. 3, 0, and -4. We plot this point. To plot this, we first count 3 units on the x-axis, on the positive x-axis. The positive x-axis is this one, and the negative x-axis is this one. This is positive y, this is negative y. This is positive z, and this is negative z. Okay? Now, we count 3 units from the origin to the direction of positive x-axis. It's 1, 2, 3. This is 3. Then, in this direction, which is y-axis, we don't move because y is 0. Y is 0. We're still in here. We are still here. Then we don't move along y-axis because y is 0. And -4, look, it is somewhere here. Then from this point, we go 4 units to down. 4 units to down in the direction of negative z-axis. Okay, 1, 2, 3. Let's say this is 4. So here we get this up to here. From this point, we count 4 units to down in the direction of y in negative y-axis. This is 3 was 4x, and for y we have no movements along y-axis in the direction of y-axis, and then we have -4 for z. We move 4 units to down parallel to z-axis. So this point is This point is 3, 0, and -4. Then we plot the other point. The other point is 0, 9, and 5. For 0, 9, and 5. For x, we don't move. For x, we don't move. So we still here. Then for y, we move 9 units to the right, to the direction of positive y-axis. 1, 2, 3, 4, 5, 6, 7, 8, 9, here. We now here. And then from this point, from this location, we move 5 units to up because z is positive. We move 5 units to up. Yeah, 1, 2, 3, 4, 5. Let's see. It is somewhere here. So the point is this. This is the point 0, 9, and 5. Now we join these two. We join these 2 points. Let's join them by different color. This is the straight line. This is the straight line. Okay? This plot of the straight line. Now it says find the position of vectors r of 0 and r of 3. So r of 0 is this one. So the position of r of 0 equals r of 0 is 3, 0, and -4. Look, when t is 0, we get 3, 0, and -4. And the position of r of 3 is 0, 9, and 5. This is the position of this point where r2 is 0, and this is r of 3. This is r of 0. These are the positions of those 2 constant vectors. Okay? This is answer for the first example. For the second one, it says find a vector valued function of a straight line which is parallel to this vector and passing through this point. Here we apply the above rule. We said to find the vector value function which represents the equation of a straight line. We apply this rule. We says the vector from the origin to point A, the vector from the origin to point A plus t times the vector value, the vector d. Okay. Here we say if we have a straight line which passes through a point and parallel to a vector, we use the point and the vector which is parallel to the straight line for obtaining equation of the straight line. Here we have given d is I plus 2j plus 3k. D equals I plus 2j plus 3k. And the point is 3, 1, 0, 3. One, 0, 3. Yes. It says find the vector valued function which represents the equation of the straight line which is parallel to this vector and pass through to this point. Here, this is A. This is point A. First, we should find the vector from the origin to A. From the origin to A. We say OA is the origin is 0, 0, 0. And this is A. So it's 1 minus 0, 0 minus 0, and 3 minus 0. Okay? 1 minus 0. We just subtract the components. Okay? 1 minus 0, 0 minus 0, and 3 minus 0. We subtract the components of the origin from the components of point A. This equals to 1, 0, and 3. Okay? And you could write down as I plus 0j plus 3k. This is the vector OA. And we should find T times D. We multiply each component in D by T. We get T times I plus 2j plus 3k, which equals to Ti plus 2tj plus 3tk. Then we say R of t is the vector valued function which represents the equation of the straight line. It equals to OA plus T times D. We found these both. OA is I plus 0j plus 3k. Then plus T times D is Ti plus 2tj plus 3tk. Now we find the sum of these two vectors. We just find the components. This equals to I plus Ti equals 1 plus Ti plus 0j plus 2tj is 2tj plus 3k, and 3tk is 3 plus 3tk. This is the vector valued function which represents equation of the straight line. This is the required. We now have another example. It says, find a vector valued function of a straight line which passes through the points this and that. Here we have given only 2 points. We have given only 2 points. It says the straight line passes through these 2 points. Here we must find D. We must find D by ourselves. Okay. First, the points are 1, 1, 1, and the other point is 7, 2, 3. We let A to be 1, 1, 1. We pick one of them to be A. We pick any of these 2 points. We pick any of these 2 points to be A. Then OA is 1, 1, 1, which equals to I plus J plus K. هل كي لم دو بوينت وبرين بقى أي بوينت okay. أو بوينت كمان أنا أقول بقى أي كبريتيلا يك ناقص صفر هريك يك ناقص صفر هريك بقى أوريجين ليدر كي هر أكاتوكوي أما فيكتورا كمان. This is OA. Now we should find T times D, but here we have not given D. We have not given D. We say D is, let's say this is B. if this is B, it is B A. It's B A. D is the vector that you obtained from these 2 points. It equals to 7 minus 1. 7 minus 1. 2 minus 1. 3 minus 1. This equals to 6i plus j plus 2k. This is D. Now we should find TD. T times D. This equals to 60i plus TJ plus 2TK. Now we have T times D, and also we have OA. So equation of the straight line, or the vector value function, which represents the equation of the straight line, R of T equals OA plus T times D. This equals to I plus J plus K plus T times D is 6TI plus TJ plus 2TK, and this equals to this is I, and this is 60I. It is 1 plus 60I. It is this equals to 1 plus 60I, and these two, TJ plus TJ, 1 plus T times J plus K plus 2TK. This is the vector valued function, which represents the equation of the straight line, which passes through those 2 points. ليرة لقى 2 point يا بعد زخوان شكل point كان ورقني بأي أو كان بابي بيت لأوريجينو أو point شيء دوزينوا أو أي دوزينوا إنجا بدو point كخويان شيء دوزينوا دي أدوزينوا كدي ما نهبو أو إيش ما هبو دي زربيتيا كي لقال أو أي وريكي بيكو كأنا كانوا أبيت شيء أبيت أبيت vector value function كشيء أنوينيت هاو كشيء straight line كان. Sorry. We still have 10 minutes.